So we had previously talked about how we can use polynomials to design cams, but we really just talked about it at a high level. What I want to do now is do a little bit deeper dive into using polynomials for cam motion design, and specifically we're going to be looking at an application where we have a cam that needs to have a low dwell and then rise and fall, but does not have a high dwell as well. So previously we have been going low dwell to high dwell and designing the rise and fall segments. Now we're just going to have a single rise fall that we're going to be taking care of. So here's the task at hand, that rise, fall, dwell, single cam. And where do you see these? Well, a very common application is in the valves of an engine where you have a cam that's driving the valves, perhaps an overhead cam or a push rod type of mechanism. But you have a low dwell, so as the combustion is taking place, you want to have the valve closed, and then you want to open and close the valve relatively quickly to allow your air and fuel into the engine or your spent exhaust gases out of the engine. And so you have that rise, fall, and then a long dwell during the combustion process. So our task will be over 90 degrees of cam rotation to have 1 inch of cam rise, or 25 millimeters, 1 inch or 25 millimeters of cam fall in the next 90 degrees, and then dwelling from 180 degrees to 360 degrees of cam rotation. That'll be our objective. And you might say, well, how about if we take some of the profiles we had learned about before with our double dwell mechanisms and apply those? That might be an easy way to do this, where we have a double dwell rise profile, a double dwell fall profile, put those together, and we can achieve this task. And it would work, where I have the profiles right down here, where the S is the position profile, and you can see that we're going from a position of 0 here on the left, going to our full rise, that might be 1 inch, and going back down and having our fall. We've got velocity profiles, acceleration, and finally the jerk profile. Now, this does achieve what we need it to do, but it's not optimal. Why is that? Well, we know that we're matching all the boundary conditions of the dwell like we should. We have S, V, and A all being 0, such that they match the dwell that we're going to have. So we have not violated the fundamental law of cam design. But what we are doing is that we are forcing the acceleration equal to 0 at that center node. There's no reason for us to do that, and what it does is it causes the magnitude of the accelerations to be greater. So this happens to be a cycloidal rise and fall, but you'll see that if we use really any of the other double dwell profiles, we get a similar behavior where we're forcing that center node to be equal to 0, because those profiles were designed to have a dwell segment right at the end of that rise or at the end or at the beginning of the fall. So let's take a step back and try to design a polynomial that will take us all the way from 0 back to 0 and have the desired rise in the center of that. So now let's define this polynomial that's going to take us through the rise and fall segment of our cam. We're going to define this polynomial, and kind of a few rules of thumb is that, first of all, we want to minimize the number of segments. So before we were talking about, let's take one segment for the rise, one segment for the fall, and then I've got my dwell segment. Well, instead of having two different segments there for the rise fall, we're going to do a single segment that takes us all the way from a position of 0 to the final position at the dwell. So here is my position plot. So as I look at it as a function of theta, and I'm going to go up to 180 degrees that I'll call beta right now. So this will be my position plot. I'm going to start at 0, and at beta I'm going to be at the dwell height of 0 again, and at the middle I'm going to be at 1 inch of height. So that'll be my position plot, and I'm going to do all of that with a single polynomial. That'll be my whole segment. The other kind of rule of thumb is that we want to minimize the number of boundary conditions that we have. So I'm going to start here, and obviously I have to have my position boundary conditions, but then we start to talk about what other ones do I have to have. Now the fundamental law of cam design tells me that I need to have not only the position but also the velocity and acceleration be continuous through the entire range. So since I'm matching up with a dwell segment, I have to have 0 velocity and 0 acceleration at the two ends. So then this will be my, so I've got theta here, this will be the velocity plot, and I'm going to have a boundary condition of 0 right there, and at a value of beta, I will also have 0 velocity. And then finally, I will do the same thing now for acceleration, where I will set up, so this will be theta again at a value of beta. I'm going to be at 0 and 0, and again, this is acceleration. So those are the boundary conditions I'm going to set up for this polynomial I'm going to construct. Now we could also create another plot here for the jerk, and I could constrain the jerk to be 0 at the two ends as well. but we're going to find that gives us a much higher order polynomial. And the problem with having a high order polynomial is we get a lot of numerical oscillation, or a lot of oscillation in the profile, which then can cause problems that we really don't want to have in a CAM oscillating back and forth. So we want to minimize the number of, or the order of our polynomial that we're going to use here. So what I'm going to do is I'm going to start off by writing the position equation for this polynomial. And you'll notice that I have 3 boundary conditions for my position, 2 for velocity, 2 for acceleration. And because of that, I have a total of 7 boundary conditions. So if I have 7 boundary conditions, I need 7 coefficients to fit. And so this will be a 7th order polynomial, which we also refer to as a 6th degree. So 7 boundary conditions forces me to need 7 coefficients to fit. So let me start off here and say that my position, S, this is equal to my first coefficient, C naught, plus C1 times theta over beta. What this theta over beta is, so beta is the segment length, so that would be 180 degrees in this case for the rise-fall. And theta is just where are we along that 180 degrees segment. So these are my first two coefficients, plus C2 times theta over beta quantity squared, plus C3 theta over beta to the 3rd power, plus C4 times theta over beta up to the 4th, plus C5 times theta over beta up to the 5th power. And then I need one more term here, C6 times theta over beta up to the 6th power. So that is my position equation. And you'll notice that I have C naught through C6. So that is 7 coefficients that I can fit for my 7 boundary conditions. Now what I'm going to do is I'm going to take the derivative of the position and then take the derivative a second time to get me acceleration. So let me go to my velocity equation first, where I can say my velocity now is going to be equal to the derivative of this. And you'll notice when I take the derivative with respect to theta here, my C naught goes to 0. I get C1 here, and then I get this 1 over beta term, and I'm going to get the 1 over beta term coming out from all of these. So I'll just pre-multiply by 1 over beta. And so I'll have C1 plus then I get C2. And one thing I missed here is that I have a 2 coming out in front of C2, so let me just sneak it in there. And this is then theta over beta plus 3 times C3 times theta over beta quantity squared plus 4 times C4 times theta over beta up to the 3rd power plus 5 times C5 times theta over beta up to the 4th power. And then my last term plus I get 6 times C6 times theta over beta up to the 5th power. So that's my velocity equation, and I get my closing bracket here for the 1 over beta. Last thing I'm going to do is take my acceleration equation, and you notice that I did mix up colors here, but these two should be connected, and I'll do the same thing with the acceleration here. So my acceleration is going to be, I'm going to get 1 over beta coming out of all of these terms here, so I'll get 1 over beta squared that I'll pre-multiply. My C1 disappears as I take the derivative, so my first one is going to be C2, so I get 2 times C2. I get 3 here times 2, so I get plus 6 times C3 times theta over beta. I get 4 times 3, so 12 plus 12 times C4 times theta over beta up to the 2nd power. And then I get 5 times 4, or 20, times C5 times theta over beta up to the 3rd power. And then finally from this C6 term, I get 6 times 5, or 30, 30 times C6 times theta over beta. And that'll be up to the 4th power and close the bracket. All right, so now I have position, velocity, and acceleration equations here that describe my polynomials. And the reason that I took these derivatives is because I have boundary conditions on these derivatives as well. So let's look at what those boundary conditions will now do to us. So I can look at what happens at a value of theta equal to 0. When theta is equal to 0, I can look at this first position equation and say, all right, let me set theta equal to 0, this one equal to 0, and so on. So all of these other terms, C1 through C6, disappear. So at that condition, I get S equal to C naught, which is equal to 0. So right away, we can say that my C naught is equal to 0. When I go to my velocity equation, and again, I set all of these equal to 0. That's the left side of that boundary condition. When I do all of those equal to 0, all of them disappear, and therefore I only have C1. And I get that the velocity is equal to C1 over beta, which is also equal to 0. So I've got two coefficients now that have disappeared. Same thing happens for acceleration, where I can say my acceleration when all of these thetas go to 0. When all of that happens, my acceleration is equal to 2 times c2 over beta squared, which is equal to 0. So c2 is equal to 0. So all three of these first coefficients are equal to 0, which means that I only have 4 coefficients left to solve for. So what I'm going to do is I'm going to put them in matrix format and then bring them into MATLAB so that I can solve them. So let's set up the matrix here. So my matrix format that I'm going to set up for the last 4 boundary conditions is going to be looking like this, where first of all I'm going to tackle that intermediate position node where I've got a lift of 1 inch in this case. And the way I will do that is I'll set up, first of all, the position I get 1 over 2 to the 3rd power, 1 over 2 to the 4th, 1 over 2 to the 5th, and 1 over 2 to the 6th. And this is the top row of my 4x4 matrix that I'm going to be creating now. And that'll be multiplied by these coefficients, my unknown coefficients, the last 4 that I don't know, where I get C3, C4, C5, and C6. That's a C. C6. And these are then equal to, in this case, the lift that I want, which would be H, which is equal to 1 inch in this case. All right. So now let me tackle the other position boundary condition, which is a value of 0 at beta. So I have 1, 1, 1, and 1. So quite easy here. So in the first case, I had theta over beta being the 1/2. Now I just get it to be equal to 1. And in that case, again, I get the same coefficients, and this should be a value of 0. And finally, I then have a velocity boundary condition at the very end, and this would be 3 over beta. I then get 4 over beta, 5 over beta, and 6 over beta. And that's equal to a 0 velocity. Do the same thing for the acceleration. I get 6 over beta squared, and then 12 over beta squared, 20 over beta squared, and 30 over beta squared. Same coefficients and equal to 0 acceleration. So what I'm now going to do is jump to MATLAB, and then I can solve for C3 through C6, and then I can plot what these SVA and J diagrams look like for this polynomial that I'm forming. So I created a MATLAB script to solve the equations that I just put up on the board in matrix format. And here's what I've written. Basically, I created this the script where I first of all clearing everything, and then I'm moving down and setting up what the lift is of my cam. So I kept everything in variable format where I can set this up for 1 inch in this case, and 180 degrees of rise-fall duration. So that was our beta angle. Here's the A equation, which I'm calling it, so the polynomial boundary conditions this is the matrix that I just put up on the board. So I get my 4x4 matrix right here, and I've got it in terms of betas. And then here is the product on the right, so the lift of H in the center, and then 0 position, 0 velocity, and 0 acceleration. And then when I go ahead and I solve for the coefficients right here, so this is the coefficient matrix that I'm solving for, C3 through C6. And one thing I got to be careful about is I want to use the polynomial features of MATLAB in just a moment. And the polynomial features of MATLAB start at the highest order and go to the lowest, whereas here I was solving for the lowest to the highest. So here my order is low to high of C3 through C6. Now let me go ahead and form these polynomial coefficient vectors. So what I'm going to do is flip left to right the coefficient matrix, and that's how I'm flipping it, so I have highest order to lowest order, and then I know I need to fill in for C2, C1, and C0, which were all equal to 0 in that case. So this is my position polynomial coefficient vector. I then have a velocity vector, which is just the derivative of it. So polydir is the MATLAB function for taking a derivative of a polynomial vector. So that was taking the derivative of s. I take the derivative of the velocity, take the derivative of the acceleration, and that gets me to the jerk function. So here I have jerk, and then what I want to do is get a feeling of what is the polynomial that I actually have for my position, and that's where this pretty command comes in, and this just makes it look text-like for what the polynomial is for s, and I created a symbolic vector or symbolic variable theta to help me with that output. And then I want to go ahead and plot the SVAJ diagrams. So I create, first of all, a figure and then a subplot of the position. So x is just a variable that I'm going from theta of basically what fraction of beta am I at. So this is the theta over beta is x here. Multiply that by beta, that gives me degrees. And then the polynomial that I'm plotting of s, and again, x is my counting along there. I do the same thing for the velocity, and what I need to pay attention to is that this is in radians per degree. And then I do the same thing for acceleration, radians per degree squared, radians to the degree to the third power for the jerk equation. So I just go ahead and plot those, and let's go ahead and run this and see how it actually works. So the first thing we're going to look for is what is my position polynomial, basically solving for those 4 coefficients that I don't know right now. So I'll go ahead and run this, and I'll flip back to the main MATLAB window, and here is the output polynomial. So my 6th order term is, my coefficient is minus 64, so that was C6. And then C5 is 192, C4 is minus 192, and then I get 64 to the times theta over beta to the third power. So just clearing up one thing, I had a hard time getting MATLAB to output this symbolically, but this theta right here would be theta over beta up to the 6th or up to the 5th. So that's what I get for my output here of the polynomial. And again, all of the lower order terms were 0, and that's what we had already determined. Now let me go to my SVAJ diagrams, and this is what the SVAJ diagrams look like, where I'm starting off at a position of 0, ending at a position of 0 so that I can match the dwell. The same thing with the velocity starting and ending at 0, and the acceleration starting and ending at 0. You'll notice that unlike when we matched the two rise-fall double dwell segments where our acceleration went to 0 in the middle, here we still have acceleration even though we're crossing through our peak rise position, but we still have acceleration. So that then allows the magnitude of the other accelerations to be reduced. And then our jerk, even though we have a discontinuity here at the ends, that's still acceptable because we have continuous acceleration. We just have a step in the jerk at the two ends. If I had wanted to go to a 9th order polynomial, I could have brought that jerk down to 0 at the two ends, but we probably would have had a little bit more oscillation in this polynomial instead of the nice smooth profile that we get here. So hopefully what you've seen from this is that I can now develop a polynomial for a desired cam function, and I've used it here for just this example of trying to have a rise-fall segment. But there's no reason that we can't do this for critical path functions as well, where I maybe want to follow a conveyor belt or follow some other velocity or acceleration profile as I move through the range, not just going to critical extreme positions. So these polynomials are extremely powerful, and one thing that you're going to find is that when we start to do more complex cam design, we might have to break this up into more segments. So imagine that I could have this rise-fall segment as 2 different segments, and I could have the rise piece and then the fall piece. And the important thing between the pieces is that I match the boundary conditions through the acceleration. If I can do that, then I'm satisfying the fundamental law of cam design, and I can get good cam functions. So let's say that we're matching a conveyor belt. I'm moving at a constant velocity for one segment of it. Well, the segments coming into that better have the same velocity matching and the acceleration set to 0 if I have constant velocity. So we just have to be careful with that as we design these segments of polynomials to put together to create more complex cams.